Just weeks ago, scientists reported creating a fusion reaction where it produced more energy than it took to start the reaction. How'd they do it?
Great question. They spent a lot of money, they spent a lot of years, and they got really smart people working on the problem.
Obviously, we know the challenges we're having currently with fossil fuels. But what is the potential of this type of energy? And why should all of these students here be excited about it?
Right, so if this gets to the point of being, going from experiments to actual working reactors, then it's real. When we talk, this is what stars do, right? Energy is the currency of the universe. But you look at a star, they pump out copious amounts of energy for billions of years. How are they doing it? Fusion. So if we can do the same thing here on Earth, we have the same potential. Now, there's still some competition from fission reactors. They're getting better too. They're getting less waste with new technologies. But this one promises to not have the problems of nuclear waste. And also, it's important to recognize that there's different approaches to fusion. So one can lead to a better method, that becomes even cleaner and even more energy efficient. And there's even a possibility of one type of reactor that could give you energy out with virtually no energy in.
Wow.
Yeah.
And the byproducts?
So the byproducts, it really depends, right? So if you look at the two main types, you have inertial confinement, where you hit a fuel pellet with lasers, and there's also magnetic confinement, okay? So the problem with both of these reactors is either the fuel waste is radioactive, or they're shooting out neutrons, right? So you don't want neutrons slamming into your DNA. Let's just put it that way, right? Neutrons are sneaky because they don't have an electric charge. So they can just go wherever they want and not get repelled by the electric charges of nuclei or the electron clouds that surround them. And that can lead to, in your DNA, for example, it hits one type of atom, changes it, because what happens is once that neutron is in a nucleus, it'll decay and become a proton. So now you've changed from one type of atom to a new type of atom that's radioactive. So it's not perfect yet, but you can screen these things. If you have, say, a meter of concrete, then you can stop those neutrons from escaping, and now you have a much better, cleaner energy source.
But that does bring up the safety concerns, right?
It does.
If something were to happen and those neutrons were to escape, then you have...
Yeah, and so with internal confinement fusion, you have a cleaner system. The other problem is that the magnetic confinement one, sometimes the magnetic field just completely breaks down and dumps all of its energy in a process called quenching. And these things weigh tens of thousands of tons, right? So, all kind of badness is gonna happen if that thing blows up, right? So, there's various approaches. There's the standard magnetic confinement machine is called a tokamak. But there's another type called a stellarator, which is gonna come a generation later. The tokamak is simpler, but bigger, heavier, and not quite as efficient. But the tokamak is sort of like a stepping stone to working stellarators, which weigh much less and are much more efficient.
So the potential of clean energy is indeed real.
It is 100% real. So what they've done is a major leaps forward. Now you can go and have a dedicated facility that goes from, inefficient lasers, inefficient experimental process to an efficient process, and then you get to that point where you're getting that clean, abundant energy.
So in essence, the power of the sun can be harnessed.
Absolutely. The power, you know what I call it, because nuclear has become a bad word? Natural mass energy, right? Because, if you look at the nuclear constituents, protons and neutrons, okay? Now you've heard, a proton is made of 2 up quarks and a down quark. If you add up the masses of the 2 up quarks and the down quark, it's only 1% the mass of the proton. What's the other 99%? That's energy and the gluons, the field that binds them together. So what we're really doing is tapping into that concentrated energy inside the nucleus. So suppose the good doctor and I, President Washington and I, are protons. If you weigh both of us, right, together we may weigh 400 pounds. But suppose now you fuse us, make us Siamese twins. We won't weigh 400 pounds once we're combined. We'll weigh only, say, 360. Where did that other 10% go? That's that energy that was freed, right? Yeah. So that's the power of the sun. That's the power of a fusion weapon that we use. But instead of having an uncontrolled reaction, we now have controlled reactions that we can control ourselves and use it to our own advantage.
Does this mean the end of fossil fuels?
A lot of people will say yes, I say no. And here's why. If you think about it, I give you a gallon of liquid, and that thing can move 2 tons, 20, 30 miles really fast, okay? So fossil fuels they have an energy density and they're incredibly portable, all right? So the question is, can batteries get to the point where they can replace fossil fuels and having a similar energy density? It may not be realized in the lifetimes of you and me who are in our early 20s, but for our grandchildren, right, that very well could be the world they live in.
Well, this has been outstanding. Thank you. And thank you all for attending the first episode of Mason, Our Future Transformed.